Welcome to this video on writing net force equations. When we say we're writing a net force equation, what we mean is we're converting a free body diagram into a mathematical statement or an equation. And so that's the main idea. So whenever you get in the weeds here in the details, just remember that's what we're doing. We're converting a free body diagram into a mathematical statement. So how do we go about doing that? Well, first we have to have a free body diagram. So if ever in a problem it doesn't ask you to do that particularly first, make sure you actually do that in order to go through the next steps. So we draw free body diagrams. I have the examples from the previous video. Now we're going to determine if the object's at equilibrium. Well, let's quickly talk about what equilibrium actually is. Equilibrium means that you have balanced forces. That's one way to look at it. And you have balanced forces, or if you have balanced forces, the object is either at rest or it's moving at a constant velocity. So those are the two different cases that result from balanced forces. If you would say it's not at equilibrium, so I'll go ahead and write that one over here. So if you're not at equilibrium, what that means is that you don't have balanced forces, so you have unbalanced forces. Unbalanced forces literally means that the forces don't have the same strength, so one's pushing harder than the other or pulling harder than the other. In this case, you're not going to be at rest, you're not going to be at constant velocity, you are going to be accelerating. So that's the key phrase here. So you'll be accelerating if you're not at equilibrium. If you are at equilibrium, you'll be at rest or you'll be at a constant velocity. So you just have to make the determination. All right. Once we've done that, once we've decided if the object's at equilibrium or not, then we're going to assign a sign to each force. So for example 1 here, a box at rest on a table. Well, they told us what this is. So this is at equilibrium. I'm going to put a check on that. The next one, a box at rest on a table. Yes, again, the box is at rest, so it is at equilibrium. Let's go through these other two here. A table being pushed across a classroom floor at a constant velocity. Yep, that's equilibrium. A table being accelerated across a classroom floor. No, that is not at equilibrium because it says that it's being accelerated. Okay, so let's go ahead here and then do the next step, which is to write a summation, which is a net force equation. Now, summation just means that we're going to list out all of the forces and add them up together. Now, when we say add them up or sum them, sometimes we're adding a negative value. So that takes us back to this next step, which is to assign a sign to each force. So when we think about assigning a sign, what we mean is if we took a regular Cartesian coordinate system, we know that in that system, up is considered positive, to the right is considered positive, down is considered negative, left is considered negative. But I could flip it around, just as long as the opposite direction is always the opposite sign. So I'm going to primarily use this system. And when we get to more advanced problems, you can change it around if you want to. It doesn't make a difference as long as everything is using the same system and not changing the system within the middle of the problem. So here's an example. I'm going to take this normal force here and assign a sign to it. Well, according to this Cartesian plane, this normal force is pointing in the positive y direction. So I'm going to make that a positive sign. The gravitational force, therefore, is pointing in the negative direction. Okay. Now, could I flip this around and say down is positive and up is negative? Sure, as long as I keep that consistent within the problem. So there I've assigned the signs to those two forces. Let's go ahead and do that one over here. Well, again, this pointing in the positive y direction is going to be a positive value. These two are pointing in the negative direction, opposite that one, and they're both negative values. All right, let's do the other two down here. Well, now we've got two different dimensions happening, right? We've got our x dimension and our y dimension. So again, let's just do our little Cartesian plane here just to help us remember what our directions are. So we've got positive, positive, negative, negative. I'm going to go ahead and label these. This one's positive, this one's therefore negative, that one's positive, that's negative. Again here, same thing. Up is going to be positive in this case, down therefore is negative. To the right is positive, to the left is therefore negative. Okay, so we've done the step of assigning signs. Remember, the signs are not arbitrary once you have decided what your system is. For your beginners, make your coordinate system just the regular coordinate system that you are used to using in math. That makes your life easier. All right, now we're going to write a summation, or the net force equation. What this is basically saying is, for each particular dimension, list out the forces as a sum. And here's what it looks like. I'm including the sign here, so I'm going to say that the normal force is a positive value, and I'm going to add, so again it's a summation, so that means I'm summing up all these forces. Normal force is a positive value, gravitational force is a negative value, so I'm adding a negative value of the gravitational force. Well, that's just the same thing as writing normal force minus gravitational force in my summation. So there I've got my net force statement, and what I'm going to say is this should equal 0. The reason it should equal 0 is whatever the value of normal force is, that's the exact same value as gravitational force. That's how they came out to be balanced. So whenever you have something, a balanced force here, what that means is your net force, so F net, is going to be equal to 0. So when I sum up my forces, it adds up to 0. In other words, they have the exact same magnitude. Now over here, the same thing has to happen, but we have 3 different forces. So I'm going to go ahead and write that statement out as the normal force. I just usually start with the positive value, but you can start with the negative, it doesn't matter. So I have the normal force minus this other normal force. Now I have to distinguish between these because they're not the same. So I'll go ahead and put a 1 over here and a 2 over here just to make sure I know they're not the same value. So normal force sub 1 minus normal force sub 2 minus Fg, because they're both pointing in the same direction. So that's why they both have a negative, equals 0. Again, because it's at rest, it's at equilibrium. Now let's get to the situations where we have more than one dimension. In this case, what we need to do is write a net force for the horizontal, and we also have to write a net force for the vertical. Now you can put y and x, or x and y, sorry, or h and v, it doesn't matter, as long as you're consistent. Alright, so let's do the horizontal first. So we have a force applied, that's the positive one, minus the force of friction, and that is summed up to 0 because it's at a constant velocity. Alright, the vertical is normal force, is my positive one, minus the gravitational force, or plus the gravitational force, which is a negative value, same thing, and this is also at equilibrium. So I'm going to put 0 here. So these are my net force equations that I'm writing out. Now we get to this last one where things change around a little bit. So again here I have 2 dimensions at play. So I'm going to write here net force for the horizontal, and I'm going to write net force for the vertical. Alright, so let's start with the horizontal. We have applied force, that's positive. And then I'm going to add the frictional force, which is pointing in the opposite direction. So far this looks exactly the same as this. We have applied force minus frictional force. But now this is we're gonna write here, this does not equal 0. It's gonna equal some number because these two values are not the same. So in this case, if I said 5 is the applied force, well that means the frictional force also has to be 5 because it's balanced. In this case, I might be saying 5 is the applied force, but the frictional force isn't 5, it might be 2, in which case, again, it's not equal to 0, it's equal to some number. The vertical net force is going to be exactly the same here, and it is independent of the horizontal, and it's just balanced out. So you can have a vertical set of forces that is balanced, but a horizontal set that is unbalanced. Now, what do we write when we have a situation where it's not equal to 0? Well, that is going to be a case where it's accelerating. And so if you remember from any of the activities that we looked at before, when you are accelerating, in order to show the relationship between the force and the acceleration, what we're going to write is mass of the object times the acceleration. And that was Newton's second law, F net equals m times a. So F net is my applied force minus my frictional force. And instead of writing not equal to 0, I'm going to write equals m times a. Well, m times a is going to be a number because a is not 0. So this might be 1 kilogram times 2 meters per second squared. So when you go through these processes, go through the steps, draw your force diagram according to the rules in the previous video. Determine if the object's at equilibrium. That's going to tell you, should I make my net force equal to 0, or should I make my net force equal to a number that comes out as the mass of the object times the acceleration of the object. Assign the signs to each force before you start writing out your summation. And remember, when you're summing, you're adding negative numbers sometimes, so you can just skip that step and just write it out as a subtraction rather than an addition. I hope that helps. Do some practice problems and try to keep yourself strict on the rules and the procedure.